I'll get right into this because I've got quite a lot of material to cover. Now, why should you actually care about photonic integration? I mean, certainly the way that people were looking at the title of the presentation, it's perhaps not the first phrase that trips off the mouth. If we look at a typical UK NOF audience, though, I would lay odds that all of you are either interested in data processing or data communications. And photonic integration basically has a significant role to play in both of those areas. Now, for two good reasons, I'm not really going to focus much on the data processing aspect. First of all, I've got a 30-minute slot. I'd need a lot longer if I was going to talk about data processing. The other thing is, I know a lot more about data communications aspects of photonic integration, so that's probably a good idea for me to concentrate on that. So what is integration? Historically, we know a lot about integration from the electronics world because many, many years ago we started off with valves. Then in the 50s, solid-state transistors were discovered. And of course, they revolutionized the electronics industry because of the manufacturability of those kinds of components compared with valves. And electronics didn't stop there. It went on to develop integrated circuits, then very large-scale integrated circuits that are now so powerful, I can actually run Windows on one of these amazing large-scale integrated circuits. It's that powerful. So, unfortunately, the optical world didn't really make that progression. The optical world, for most people, is pretty much stuck where the electronics world was in the 50s with the transistor. Individual semiconductor lasers and individual components. We refer to those as discrete components. Now, that's a problem because, as you guys all know, there's a really big demand for bandwidth. Even this recession didn't really slow down that demand. That chart is indicating how much capacity you can get on a single pair of fibers historically. And that really kind of marks out the success of dense wavelength division multiplexing. So most of the growth here was achieved without photonic integration because the first commercial photonic integrated circuits, or PICs, were delivered in late 2004, the first commercial systems based on PICs. However, to continue that growth, that's an exponential growth, by the way, because you can see there's a logarithmic y-axis. To continue that growth, you really do need to increase the levels of component integration, just as we have done in electronics. So will all of this work? On the right-hand side, you've got a fiber cable. There's a bundle of fibers in there. Could be dozens, could be even hundreds of fibers in that cable. On an individual fiber, you would have many wavelengths. But each wavelength, for the most part, is lit by discrete optical components. Now, we're actually quite fortunate because small-scale photonic integration is quite well established. This is a component from probably the largest optical component company in the world. It's JDS Uniphase. And you can see on that well-manicured fingertip there, there's a tiny little sliver of indium phosphide. The material of choice in the photonics world is indium phosphide, as opposed to silicon in the electronics world. So that handful of components on the left-hand side has basically been integrated onto that tiny little sliver, which goes into a package and becomes a tunable XFP device. So XFPs, it's pluggable optics. You get your Cisco or your Juniper routers, and you can plug those kinds of modules into those devices. But that is a small-scale photonic integrated circuit. Small-scale PICs are single wavelength. It's one wavelength at a time. To really benefit from photonic integration, you have to go multi-wavelength. So in other words, instead of one, let's take 10, for example. And the large-scale PICs that were shipped back in 2004 collapse 10 wavelengths worth of capacity onto one pair of chips, one for transmit and one for receive. That transmit chip, which is the bigger of the two, is only 5 millimeters on one side. It's basically about half the size of my little fingernail. And that has 100 gigabits per second of capacity. So you can see where the kind of gains will start to kick in with this, because you've got smaller systems, you've got less power utilization, you've got much more reliability. Because one of the things that nice little animation did not show was the number of individual fibers that you need to connect discrete components together. And they're the biggest single reason why stuff doesn't work when it arrives from the manufacturer. You know, the gentle FedEx guys, you know, sometimes they break things, and those little fibers are the first thing to break. The other thing about photonic integration is that it allows something called service-ready capacity to be enabled. Now, what this is, it's really a marketing term, but what it means is bandwidth in bulk. So instead of turning up one individual wavelength at a time, you turn up many wavelengths at a time. And I want to actually, if the video works, and it did when we practiced it earlier, I'd like to show you a video now. It'll only last for a minute, but I just want to explain what you're going to see. We're going to add a single PIC-based line card into a system. That line card will basically take about the same effort as adding a single 10 gig transponder. But instead of getting 10 gigs, you're getting 10 times that capacity. What you're seeing here is, it's called an optical spectrum analyzer, and it looks at the optical fiber and it's going to tell you if there are wavelengths already on that fiber. So here, there's a lot of peaks showing there are already wavelengths running on that fiber. So the object of the exercise here is to add more capacity. And you'll see over on the right-hand side, there are some gaps. And those gaps are what we're going to fill in with the new card. In real time, this process takes 4 minutes. I've speeded the video up, but just to show you, give you an idea of real time, there's a stopwatch that you'll see there. So, okay, fingers crossed, let's all say the magic word, and hopefully this should work. Hey. So that's my boss, actually. He's plugging in the line card. I guess it's juddering because of WebEx. But what you're going to see here, the stopwatch is just about to start. It'll speed up in a moment. For the first 3 minutes, the board is booting. It contains a complete digital cross-connect, so it is quite a sophisticated device. We're now up to 2 minutes. Once we get to 3 minutes, I'm going to zoom in, and you will see on the right-hand side, the waves start to come up automatically. Now, they come up a little bit hesitantly. That's called power balancing, and the reason for that is that this is a non-service interrupting operation. So it does not disrupt the existing waves that are on that fiber. So in 4 minutes, we've just added 100 gigabits of capacity. So next time your transmission guys say, can't have that till, you know, that London to Birmingham link for another 3 months, you know, show them the video. So these photonic integrated circuits at 100 gigabits per second have been very commercially successful. This is the marketing spin slide. What you see on the chart there, the light blue line is the first company to ship 10 gigabit transponders, individual transponders. The purple line is my company, Infinera. We suddenly gained huge market share when these devices, when these systems became commercially available. But we need to go further. I mean, you know, if this is so good, why isn't everybody doing it? There has to be a catch. And unfortunately there is, because PICs were first described in a paper written by a guy called Stuart Miller from Bell Labs in 1969. That's 41 years ago. And there are lots of academic projects that have developed PIC technology, but some of you might be familiar. The nature of academic funding means that all of those projects dead end. You never really seem to be able to build on the success of those projects. Commercially then, the biggest challenge is the lack of R&D funding, because the only companies today that could build PICs are optical component companies. Optical system vendors sold their component divisions back in 2000 when they needed cash. And if you look at the total worldwide market for transponders last year, it was about $2.1 billion. Rule of thumb says that you use 12% of that sales revenue for R&D. But the problem with a PIC is it's a very high risk and high tech project. You don't spend 12% of your revenue on PICs. You spend about 1%, the advanced technology projects. That 1%, that 21 million, is divided between the 5 or 6 major optical component companies in the world. And each company will have 5 or 6 high-tech projects competing for that money. To give you some idea, the reason that Infinera was able to develop PICs is that we achieved $300 million in venture capital funding when the company was founded. And we didn't spend it all on PIC development. We probably spent about half of it on PIC development, 150 million, which is the equivalent of 7 years' high-tech budget for the entire optical component industry. That's one of the reasons why other people are not doing this. So the next generation of PICs is really going to start to push things a lot harder, because for years we've been limited in a way to 10 gigabit per second wavelengths. Now it's okay because just like Intel can't make a CPU go faster than about 2 gigahertz at the moment, what do? They put lots of cores on a slab, on a chip. It's the same thing. We put lots of wavelengths on an individual PIC, but we also need to make those wavelengths go faster. Historically, we've been very fortunate in the good old PDH days, async as the Americans refer to it. Wavelengths operated at about 1 gigabit per second. It used a modulation technique called non-return to zero, NRZ, and about 3 components, 2 in the transmitter and 2 in the receiver. When we moved to SDH, 2.5 gig wavelengths, same modulation technique, same number of components, but we're getting twice the speed per wavelength. And at 10 gig, same again. So this is a really good scaling curve. It's one of the reasons why that exponential growth that I showed you earlier was able to happen. A nasty thing happens at 40 gig. We have an explosion of optical components that are needed because, well, let me explain why. Complex modulation, which a lot of you will be familiar with, it's used in ADSL, it's used in WiMAX, it's used all over the place, complex modulation. But optical transmission is about transmitting very high data rates over long distances for very little money. Now you can stress any one of those variables, but it's a bit like a balloon full of porridge. If you squeeze it in one direction, it'll pop out somewhere else. In other words, if you try to transmit more quickly, you won't be able to go as far, or it will cost you more money. Now, our biggest problem here is optical fiber because it has lots of nasty things going on inside it. Loss, dispersion, nonlinear effects. And if you were able to wrap your arms around all of those properties and give them a magnitude, you would find that that would scale with the square of the symbol rate that you're trying to transmit at. So in other words, instead of being 4 times more difficult to transmit at 40 gig than 10 gig, it's 16 times more difficult. That's a big problem. So what you can do is change the modulation technique. Non-return to zero, fantastic modulation technique. It has served the industry well for decades. It's still incredibly effective because it's so easy to implement. But it's very susceptible to these scaling effects. So we have to move to something else, typically phase modulation. So how do you apply phase? How do you use phase to modulate an optical signal? That component there, it's called a Mach-Zehnder interferometer, an MZI, and we use that to put the ones and the zeros on the beam of light because the laser is transmitting a continuous beam of light. We've got no ones and zeros on there yet. The light is split through the Mach-Zehnder. It travels in the upper arm and the lower arm. I've color-coded them red and green, but it's the same color of light. It's the same wavelength. We can put something on the Mach-Zehnder that will modulate that signal, it will modulate that carrier. Basically, you change the refractive index of the lower arm of the Mach-Zehnder. So when the waves come back together again at the end of the Mach-Zehnder, there will be a phase difference. And that phase difference depends on the signal that you apply. So you've encoded a high data rate signal as phase changes on that wave. Now again, I've only got half an hour. You'll have to bear with me that you can recover it somehow. It's quite complicated actually to recover, but maybe next UK not, huh? Phase-based complex modulation has got 2 fundamental advantages. The first is that it's not an amplitude modulation technique, so it's constant amplitude generally, and it tends to be more tolerant of these dispersion effects and nonlinearities in the fiber. But the second thing is that by putting lots of phase states on a single symbol, you can break that square relationship. You can actually transmit more bits per baud, and that's a good thing. So how do we do that? The simplest phase-based modulation is called phase shift keying, or sometimes differential phase shift keying. Again, very basic. There are no more bits per symbol than NRZ, and the only reason that this is better is that all phase-based modulation techniques are a bit more tolerant of dispersion effects. If we really want to kick in some juice here, we've got to go to more phase states. This is quadrature phase shift keying, 4 phase states. 4 phase states encodes 2 bits per symbol. So this is quite an advanced modulation technique. We could put more phase states if we wanted to. Remember in DSL, what have we got? 64 QAM and 256 QAM type things, very, very large numbers of phase states. There's a problem. you can kind of intrinsically imagine that as you double the number of phase states, you double the complexity of the circuit. But I'm only getting one more bit per baud, per symbol. So I'm into a law of diminishing returns if I try to put more and more phase states onto this. And in fact, for discrete component implementations, 8 PSK hasn't happened, just hasn't happened. It seems to be too complicated. So is there another way that we can cram more bits in a symbol? Well, we can use polarization. Remember the old advert, you know, do these Foster Grants make me look like Cary Grant's horse, or whatever that particular one was. But we use two polarization states, X and Y polarization. And each polarization has 4 phase states. That is called polarization multiplex QPSK. Alphabet spaghetti coming out here. We can go to much more complicated modulation techniques, but let me just give you a glimpse at how complicated these optical circuits are becoming. That's the Mach-Zehnder that I showed you earlier on, and you can do phase shift keying with 1 Mach-Zehnder. With 2 Mach-Zehders, in this kind of structure, it's called a super Mach-Zehnder structure, you can do quadrature phase shift keying. You can double the circuit again to add the 2 polarizations. This is polarization multiplexed QPSK. Well, that is currently the state of the art in terms of 40 gigabit transmission. That's a really good modulation technique. One of the reasons it's very attractive is that it operates at 10 gigabaud. It's the same baud rate as 10 gig NRZ, so you have the same design rules in terms of reach, optical reach, as you would at 10 gig. Fantastic. Also, you'll notice the 4 signal inputs, the little blue blobs, each of them runs at 10 gigabits per second. And 10 gig electronics is cheap. So this is a very attractive implementation. Later on today sometime, I think we have a 100 gig Ethernet presentation. Now, 100 gig Ethernet is about sending very fast signals over short distances, 100 meters maybe, or maybe 10 kilometers. How do we send 100 gig over the Atlantic Ocean? What kind of modulation technique would allow us to drive a signal 3,000 miles? Option 1, we could stick with that modulation technique that was so good at 40 gigabits. But the problem there is the electronics would have to run a lot faster. You put a huge strain on the electronics if you just turn up the baud rate. And also, the reach won't be as good because you're increasing the baud rate. Option 2, we can find some more phase states. But remember, there was that law of diminishing returns. Interestingly, you can solve it using photonic integration. You know, just like we're not afraid of putting 4 cores on a chip, we shouldn't be afraid of putting large numbers of optical components on a chip. Option 3, we could find another modulation property. I'm calling it spread spectrum. It's a bit weird, really, because, of course, we're using spread spectrum anyway in WDM. But the way this happens is we take that Pol-Mux QPSK signal that worked so well at 40 gig, and we just double it. But we now have 2 wavelengths. And we put the wavelengths in the equivalent of a 50 gigahertz slot on the fiber. So in other words, that 100 gigabit per second signal is occupying about the same space as a 10 gigabit per second signal does today, which is very good. It means we're getting a lot more capacity in the optical fiber. That is our 400 gig PIC Transmit Module. I apologize that on the PDF that you'll be able to download, I've had to blur that out because there are some proprietary details even in that diagram, strangely enough. One of the beautiful things about PICs, you can see, I'm going to have to just walk over here. These are the only fibers in that system. If that was implemented in discrete optical components, there would be 250 tiny little bits of fiber. Now, what's going to be the dead on arrival rate for a board based on those kinds of fibers? This is the receive module and a list of all the kinds of components that are in that module. That's the kind of power of integration that we're getting to today. Interestingly enough, if you add all the numbers up, you're getting about 500 or 600 components on that thing, which is almost as many as the Intel 4004 back in 1970. So we are kind of catching up on the electronic world. Now, I put these 2 slides at the end, in case I had time to do it. I'm okay for another 5 minutes, Nigel?
I think so.
Yep. Because a lot of you will be wondering, why indium phosphide? Why don't we just use silicon for this? Because silicon is a fantastic material. So apologies, I'm going to have to give you a quick refresher on semiconductor physics. So semiconductors, right, this is a material that sometimes it conducts electricity and sometimes it doesn't. But the important thing about it is we can choose when it conducts electricity or not. We can electronically turn it into a conductor or an insulator. And, well, conductors are materials where the electrons are free to flow between atoms. Insulators, the electrons are basically tied to a given atom or molecule. A semiconductor, if the atoms are tied to the individual atom or molecule, we say that they're in the valence band of that material. They're basically whizzing around the nucleus. If they can be liberated, they move up into the conduction band, and they can now move around that material. The difference, the energy difference between the valence band and the conduction band is called the band gap of a semiconductor. And you give it a kick, an energy kick, and the electron is promoted up into the conduction band. What you see here is a direct band gap semiconductor. It's where the minimum in the conduction band is directly over the maximum in the valence band. That kind of implies that there is an indirect band gap semiconductor. And that's where the electron has to turn right on its way up to the conduction band. That's a quantum physics term. What it actually means, if you look at the axes on those diagrams, the y-axis is energy and the x-axis is momentum. These are two different quantum mechanical mechanisms. So what are the odds of the same electron experiencing an energy change and a momentum change within the kind of time scale we need for this to happen? Well, they're lower, right? The odds are lower. Materials like indium phosphide, gallium arsenide, cadmium telluride, SIGs, which is a thin film photovoltaic material, these are direct band gap semiconductors. Silicon, germanium, aluminium arsenide, many other. I mean, there are hundreds of materials that can act as semiconductors, and some of them are direct, some of them are indirect. For our discussion here, the only thing you need to know is that direct band gap semiconductors make good lasers and photodetectors. Indirect materials do not. In other words, it's very difficult to get silicon to lase. There's an awful lot of money being spent right now on very clever people trying to get silicon to lase, and they haven't made it yet. I'm not saying it's never going to happen. It's like, you know, maybe I will get a date with Jennifer Aniston. But in fact, there is a quantum universe where right now Jennifer is sitting in the front row saying, I really dig these cool PowerPoint animations. But sadly, it's not this universe. And in this universe, we haven't yet got silicon to lase. So, just in summary, photonic integration is solving serious problems in data processing. I haven't covered those aspects, but the whole issues of optical computers are basically hinged around silicon photonics. Silicon, you can get it to work, but only over very short distances, on a chip or perhaps across a backplane. If you want to drive thousands of kilometers, you have to use direct band gap materials like indium phosphide. And it's at the very beginning of its technology cycle. You know, I said we've almost got to the point where Intel was 40 years ago. So in the words of the famous philosopher Frank Sinatra, the best is yet to come. Thank you very much.
Thanks very much, Jeff. Any questions for Jeff? He lost me about halfway through.
How are your editors doing on PIC technology?
We are keeping quite a close eye on that, as you'd imagine. There are a couple of aspects to this. You know, maybe we could even talk about it offline, but we do believe that there is one particular competitor from China that could well do, and we think they're fairly close. They're not building those PICs themselves. They've got an American company to do it, but you know, they're probably the closest to it. There's a trick with any kind of integrated circuit, and that's yield. The yield that you get from those slabs of indium phosphide or silicon really determines whether you have an economic process or not. And we've got a 5 or 6 year head start in terms of getting these things to be economical. So even if you can do it technologically, it's not clear that they can catch up, from the commercial yield side of things. And that is the PIC that they're designing isn't actually quite as good as the one that we shipped 6 years ago. I would say that though, wouldn't I?
Any other questions? Well, thank you very much indeed, Jack.
Thanks, Simon.
Very interesting.